All right, so design optimization. So what is design optimization? So of course there are conventional ways. Okay, so of course conventional will be more towards trial and errors. Okay, of course you could when you come up with designs. Okay, you have this initial design, then you can perform analysis, right? I mean, different type of analysis, finite element analysis to perform, then to evaluate whether your analysis fulfill your design criteria or not. So if no, then probably you want to change your design to fulfill that design criteria. So how to change your designs? Okay, of course, conventional way is basically it could be my guess, okay? It could be basically uh, based on the result itself, you think, yeah, increase thickness or increase the length will help in terms of fulfilling the one of your design criteria, something like that. So it's more towards very subjective, okay? Then it could be sometimes very time consuming, okay? Because you do not know, sometimes you don't know where to actually change, okay, your design to fulfill that design criteria. So it could be very costly also in that case, right? So more productive or more objective ways, and what we can say cost-effective way will be that numerical optimization techniques, right? So again, it basically is the same thing. So okay, it's basically same like what we are doing. I mean, like what the conventional way. So, but it is more so-called structures, okay, and it is also trial and error, but it's not by a guess, okay. It is appropriate structures of trial and error case, okay. So from that optimization itself, okay, it will basically also gone through. It will also go through uh, a set of simulations, basically with a different design, design. Let's say your dimensions. Okay, it will also go through a different a set of simulations. Then from there, okay, it determine the optimums. Let's say your your so-called parameters, okay, to be, or the dimensions in to be used in your design in achieving a design criteria. Of course, we can, for example, if a conventional way, all right. So if I want to the current safety factor, let's say I'm using safety factor as my design criteria, right? So we found that the safety factor now is 1, right? So then if I want to achieve 2, I would want to increase the thickness. Okay, so increase the thickness. In this case, we do not know how much we want to increase. The current thickness is 2, so probably we know that increased thickness will increase the safety of factor of safety. So we increase to 3. Okay, so we try 3. No, it is still below 2. 4 is still below to 5. Okay, it's almost to 6. Then it is above 2. So it is between 5 and 6. Okay, so in that case, if we go one by one conventionally, then probably we perform a different set of these so-called thickness. We perform the simulation with different set of thickness. Then probably we will find one thickness that is optimum, that give me that fulfilling the design criteria. So that is a conventional way lah. I mean, you have to do vary with your what we call your thickness in this case, then to rerun the simulation again, then to find your so-called thickness that can fulfill the factor of safety of 2. Okay, so this numerical optimization also something similar. Okay, uh, it will also run a set of this simulation from, let's say, from your thickness 2 to 8. Okay, but of course depends on how it will choose. Okay, from 2, will it run 3, will it run 4 thickness, 5, 6 until 8 by 1. So it will have a so-called a more uh, uh, so-called more structures, so-called of simulations lah. Basically, it won't go for all, okay, but it will find a certain numbers out, okay. Then from there, they build a relationships. Then from there, they know from 2 to 8 thickness, then what is the optimum numbers that can fulfill the factor of safety 2. So in the case of you want to fulfill factor of safety 2.5, also from if you run this set of simulations, then also it can help us to determine what is the optimum numbers, right? So that is more structures with a better planning on how to achieve our design criteria. So here we are saying that it's more productive or cost effective comparing to the conventional way where you have to by guessing, or probably you have to do a lot of many sets of simulations to achieve that, right? So that design optimization, okay, either conventional way or what we call the numerical optimization way, also basically you follow this particular flow. So initial design, so if you have an initial design, then you will perform your analysis. So here we are talking about static analysis, dynamic analysis, because more towards our solid mechanics related problem. So from there, we'll evaluate whether the result is good or not, the stress is very high or not, the factor of safety is okay or not, deformation is within the design criteria or not. So if no, then probably I would want to improve. Okay, so improving by changing, modify the designs. Okay, if yes, if evaluates, okay, can the design, so if probably will come down to here, can the design be improved, okay, or is already fulfilled, then basically is your final design. If no, then probably you need to modify your design, change some dimensions, then perform again, then evaluate again. If everything is good, then final design. If no, then you have to go until you get a very good design. Okay, so conventional way and also the design optimization way also basically fulfill following this particular flow. Right. So here we are we will be covering two types of optimization methods. The first one is what we call topology optimizations. The second one will be what we call parametrics optimizations. So what is topology optimization? So a lot of time when we about to start, okay, the designs, okay, we want to come out with a design. So it is this topology optimization. I mean, we do not have any idea what the shapes will of my design is going to be look like. Okay, so topology optimization basically will help designer to have a particularly better initial what we call the design concepts. Okay, our concept design itself. Okay, so for example, if you have a case of this itself, a bridge. Okay, so you could have what we call this particular original shape itself. Okay, we do not know what is the optimized shapes. Okay, so of course these will be the it could be if you have seen here, right? So the original shapes, it could be something similar, but we do not know what will be the optimum. So what performing this topology optimization, basically it will help us to have a better idea, okay, what should be the shape of this bridge look like, okay. So those that unwanted areas or unwanted space basically could be actually removed, okay. That usually is to the whole idea is to give us a better idea of how our design should look like. The shapes of our design should be looking like by the usually is more towards minimizing the weight itself. Okay, the objective is more towards minimizing the weight itself. Okay, so the goal of this topology optimization is to find the ideal distribution of materials with the predefined design space for a given set of loading and boundary measure. Of course, we have to set, okay, For example, this bridge, I have a boundary fixed at here, then we have a loading a lot on the top surface itself. So this must be kept. Okay, this particular part must be kept. Okay, this particular part have to be kept because we have to fix here, fix here. So by performing this so-called topology optimizations, okay, by minimizing weight itself, so we will have an idea, okay, how a shape of this bridge should be look like. Okay, so in this case, the region that contribute the least to the load itself, I mean, can be actually removed. Okay, the whole idea is to minimize the weights. Right. So if from this case, okay, originally our design is like that, then by performing topology optimizations, okay, with the objective functions of minimizing the weight itself, then probably you will see that actually this particular center part is not needed. So in this case, you have an idea, okay, what your design should look like. Okay, so probably it's a curved shape like this, then fix. I mean, of course, you have a fixed boundary at the both end, then you have your loads on the top itself. So you can see that here will be not needed. Okay, in terms of supporting the entire weight itself. Okay, so supporting the entire load itself. So from here itself, if you come out with the output of this topology optimization itself, so basically it will help us to see, yeah, my designs, okay, will probably should have these particular shapes itself in achieving so-called weight minimizations objective. So is this good enough? Okay, basically topology is a first step. So it gives us an idea, right, for our design concept. So from here itself, so we can follow this the outcome of this topology optimization to design our so-called our structure, our model itself. Okay, so in this case, the bridge itself, it should be designed something similar like that. Okay, so once we have this good design concept, so probably we have to further, we can model it out. So then of course we have to go through a proper analysis, static analysis, dynamic analysis, or whatever failure analysis to determine whether this design itself is sufficient to take the loads in terms of static, thermodynamic, or whether we will fail or not. Okay, so that is the first step. Okay, from the topology, you get the shape, okay, the optimum shapes. Okay, then probably you can making use of these optimum shapes to have your design. Okay, have your initial design. So once you have your initial design, then it come back to here, right? So you perform analysis, evaluate result. So if it can be improved going up, if no, then that is your final design. So how to go through this? We have another so-called optimizations called parametric optimization. So parametric optimization basically is vary the variables with design parameters. Okay, the design parameter become is a variables. Okay, basically you change the design parameters. For example, your length. For example, your thickness, your height. So you can change all these parameters. Okay, with the aims of getting optimums these design parameters, okay, or design variables, okay, that fulfill our objective. Okay, so here is talking about design constraints. Okay, so here parametric optimizations basically help designers determine the optimum shapes and dimensions. So it's more details analysis in this case. So one topology is more in terms of concepts. Okay, once we get the shapes, so we can come out with that particular designs. Okay, so once we have the design itself, then we have to perform a proper analysis. Okay, here to determine whether it fulfill the design our design criteria. If no, then we perform parametric optimizations. So the whole idea is to get help the designer to get the optimum dimensions. Okay, of our model or our structure during the final stage design. Okay. So here we have a few terms to be used. Okay, later on you will see we talk about design. That in terms of this parametric optimization, we use certain terms. So the independent variable whose value can be changed to improve the design is called design variable. So that design parameters, like for example your length, your height, your thickness, okay, the distance between these two components, all these are related to the parameter that can be changed, okay, to improve your design. So here we term it as a design variable. So it could be length, thickness, or any point that can change your design shapes, right? So these parameters is a variable that we will use to change to achieve our objective. Okay, then the response of the designs to applied loads are what we call state variables. Okay, so this is a variable that basically is related to response. So we want to use, it's basically our output itself, okay? More towards our deformations, our frequency, our factor of safety, our stresses, our temperatures are all the output, okay, of our analysis. All right, so this is a response of our design. So when you apply with the fixed boundary, with the applied load itself, what is the deformations, right? So this deformation is the output, okay, of the response, okay, subjected to this boundary and load itself. So here we call it state variables, okay, or response of the designs. Okay, so we have the input, we have the input, which is what we call here is the design variables. We have the output or the response, which is what we call state variables. Then probably we can set our design constraints, okay, for optimization. So the restriction placed on the design are the design constraints. So we want to achieve the constraint on our state variables, okay, our output, our response, the constraints. Okay, so for example, here we want to achieve, oops, what is this? We want to achieve our so-called, for example, our state variable is stresses, right? So the equivalent stress is like that day is 200 somethings, okay? We want to achieve the equivalent stress below 150, for example, okay? So that basically is our constraint on our so-called state variables that used to achieve our objective. Okay, so that is our design constraint itself. So sometimes this design constraint could be also is like the topologies. We further minimize the weight itself. Okay, the weight itself also can be our design constraint itself. Okay, so it could be our constraints and also the objective functions. All right, so the whole idea is minimizing these objective functions of this design variable subjected to a given set of design constraints. So what we are doing here, or this parametric optimization doing here, is basically, okay, given given your design variables, I mean, let's say your length, thickness, okay, you change your design variables, okay, in this case, okay, to fulfill, okay, the design constraints, okay. So minimizing that objective functions to fulfill that so-called the design constraint. In this case, is the constraint on your state variable. Could be the stresses, deformation, temperature, and frequencies, right? So that is parametric optimization. Okay, so parametric optimization basically is also basically is the use of your models, okay, to find the effect. Basically, it built this parametric optimization. Basically, it built the relationship between your design variables and also your state variable or your response. So here you're talking about the input and output. So you have the in, you have out, then probably you can build a relationship between this in and out against. Okay, so this parametric optimization, the whole concept is like this. So basically, it give you a set of given a set of inputs. Here is a design variables. So basically, it perform the corresponding sets of what we call the output. Here is response, or the state variables. Then from there, okay, it build a relationships. From this relationship itself, then it can find where is the optimum so-called dimension, or your where is your optimum dimension or optimum designs, okay, to fulfill, okay, because you have built the relationships, right? Because you have a set of input, with a set of output, you have basically the relationship between this in and out itself. Basically, you understand this particular model itself already, the behavior of this model itself already. So from there, if you have a set of design criteria, so basically it can find, based on this relationship that you have built, it can find the suitable inputs, okay, the suitable input that can fulfill the constraint set on the outputs itself, right? So basically it comes like this. So giving a set of input, okay, with this model itself, it gives you a set of outputs, okay? So here we know the information of this system, right? So with a constraint set on the state variable or the output itself, okay, with the objective function itself, okay, then it can actually find with the out and the system, then we can actually find the suitable input that can fulfill, okay, the design criteria that we set on the state variable or the output itself. Okay, so basically it's input and output so-called relationships lah. So after multiple response data set are collected from these finite element simulations, so if you have given a set of input, then you have a set of output. So a mapping relationship can be established between this in and out. Okay, design variable or the set and the state variables. Okay, so from there itself, if you have set response criteria, what we call the criteria, design criteria based on the response itself, then with this particular relationship, this is determines, then probably you can find a suitable input that can fulfill what we call the entire design variable that we set on the output itself. Right, so optimizer then explore the mapping of the parametric design space, which is this one, okay, to find the optimal set of design variable, the inputs, okay, to fulfill the given response criteria. All right, so how to achieve this? Okay, so a lot of time they use a DOE, design of experiments, are used in combination with the response surface optimizations, response surface so-called chart itself. So it's response surface modeling. So combination of these two itself, it can efficiently map out this so-called relationship parametrics design space. We call it the relationship of parametric design space. Okay, through simulating a minimum number of design scenario. Okay, so this design of experiment, basically it will come out with tables. Okay, DOE table that choose, okay, it will come up with a minimum this design scenario. Okay, the input, it will choose a minimum design inputs that come up with this design output, what we call the response. Okay, from this design of experiment itself, basically it will come out with a minimum number of design scenarios. Okay, referring to the minimum number of design variables. Not it basically optimize. Okay, it find optimum numbers. Okay, that for the simulations. Okay, to build this so-called parametric design space or the model itself. Right. So with a minimum set of design variables. Okay, then it will run to find the response that corresponding to this minimum set of design variables. Okay? So from there, they can build what we call parametric design space through what we call here response surface modeling. So once we have this response surface modeling itself, right, then we can find, okay, subjected to the constraint on the output or the response, we can, based on the response surface modeling, which is relationship models, then we can find the optimum number that can optimum numbers or optimum values based on this response surface itself to find the optimum values that fulfill the design so-called criteria that we set on the response itself. So this optimal value basically will be usually is the optimal value for our input or design variable itself. Okay, so this parametric optimization, commonly they basically combining this DOE design of experiment as well as response surface modeling. So what we are doing later on is also based on this design experiment and response surface optimizations. So what is design of experiment? Okay, so basically it find, okay, simulated response, fit the simulation response data to the mathematical equation to predict the response. So what what it does is basically it come out with a set of design variables, the inputs, okay? Then it find, okay, through the simulation, it find the response, okay? The response, you simulate the response due to this set of design variables. So the response could be the deformations, okay? So for example, I put my design variable as my thickness as my design variable, thickness, height, okay, and the width itself is my design variables, okay? So I would want to my response or my state variable now output is deformations, okay? So the design of experiment basically come up with a set of combinations of these design variables. So the thickness, height, and also the width itself, okay, at different values, okay? A set of these design variables. Then to simulate the deformations, right? So in this case, so for four input variables, let's say I have 4, okay? So if you have only 2 levels each, so you have a total of 16 experimental runs are needed, 4 power of 2, okay? So it's 16, okay? So in this case, so basically you have X, you see that the first set, okay, the first set will be 0, 0, 0, 0. Then we have, because the 2 level means each design variable have 2 levels, so 0, 1, 0, 1, 0, 1, 0, 1. So here we'll have 16 combinations, okay, total of 16 combinations of experiment to be what we call the simulation to be run. All right. So once you have run this simulation, so probably we can run the simulation. Here is referring to a deformation. We determine the deformation based on a set of these inputs, okay, design variables, different set of design variables. We have a deformation due to this design variables, okay, the output talking about the output itself. Then from there itself, we can build the what we call design space or the parametric design space itself. Basically is the model itself, okay? We understand the system, all right? So if you have just 4 design variable, 2 level, then you see that you have a 16 experimental run, okay? Basically to complete, right? If you have more, okay, talking about number of levels, if let's say you have 2 design variables, 4 design variables as you've seen here, x1 until x4, each of them probably you have 4, then you have a 4 power of 4 levels, so you have a 4 power of 4, right? So 4 power of 4, then you have 256 these experiments to be run. Okay, so it could be very time consuming. Basically, you are running all these 256. From there, you find relationships. Okay. So what it can do, okay, if you are doing this, so it's something similar like conventional. Like if you are doing conventional, also you can do like this. Okay, you have a total of for example, you have total of 16. You run 16 times. You run your simulation with 16 times with different design variables. Then you find the deformation. Then from the list of deformation, you find a suitable design variable that can fulfill your design criteria or constraint. All right. So here in ANSYS, this design of experiment it could be further optimized lah. So if you have just now four inputs with 2 level itself is total of 16. Okay, so undergoing this design of experiment in ANSYS, for example, this central composite design CD is a popular design. Basically, it will provide a minimum number of required experimental runs. Okay, so you do not really need to run all full sets. Okay, so it will through this itself phase center CCD itself. Okay, so it will, or CCD itself, it could help us to find to determine the optimum number or minimum number of experimental run to run. So you do not really need to run the full set of design of experiments, combinations of design of a variable itself to complete the so-called, to find or determine the so-called design space. All right, so phase center CCD, for example, in this case, you have 3 design variables at 3 levels at each of them. So it's 3 power of 3 is 3 power of 3 is 27. Okay, you have 27 set of experimental runs. Okay, but then if you are putting the using this phase center CCD or central composite design itself, okay, for the optimization of your experimental runs, so instead of 27 experimental runs, so you only need 15 in this case. Okay, so it will help us to minimize the number of experimental runs. So you do not really need to run the full set of these experimental run. In this case, let's say you have 4, 2, then it's 16 set. Then basically you need to run all 16 to find or to build the design space or the model or the parametrics model itself. Okay. So once you have done this optimum or minimum number of experimental run from the design of experiment, right? So then you can actually, you have the in, you have the outs, okay? At its minimum number, then we can build the relationship or design space, okay? Here is through response surface optimizations, okay? Response surface modeling. So at this response surface modeling, basically it plot, a response surface plot lah, basically over your different design variables. Okay, so after the design space is sampled, okay, response data set, okay, can be already obtained for a design criteria through a finite element simulation. So this is what we have mentioned just now. Okay, so once you have a response data from that design scenario, here is minimum design scenarios through this central composite design CCD. Phase center CCD itself, you can get a minimum design scenario to get a response set to sample that design space. So the response data set, which each data set corresponds to a simulation scenario, and then used to fit the response surface model. So basically from these results, the in, the design variable, and the out, the response itself, we build there's relationships, okay, through this what we call response surface models. So from response surface model itself, actually we can find, okay, where let's say I want my response, let's say my deformations at around 20, okay, so at 20 itself, so let's say my basically from the response surface itself, we know that at 20, let's say my response, I want it to be at 20 itself, so you know that your basically your what should be your design variables okay, from this particular case. Below 20 itself, so all your design variables should be in this particular so-called regions, okay? 8 to 5 probably, okay, or 9 to 5 until here 1 to 1 point, okay? Sorry, here, yeah, here you know that is around, from here you know around, it's in these regions, okay? Is in the is, if I want to, if we can build this response surface, basically it helps us to have a so-called continuous variations of the response, okay, with respect to the design variable. So basically we know that if I want here 20 below, okay, so basically is anything that in this particular design variables, okay, in this particular design variable, I have any response that below to 20, something like that. All right. So that once this is built, okay, so we can set what the constraints, right? Because we build the relationship between the in and out. Here is a design variable and response or state variable. Then we can set the design constraint. So the constraint on the state variable. So if my state variable is the deformation, so here I want to set my deformation below 20. So what will be my design variables input? Okay, so that is from here we will find where is it. Of course, based on this particular mapping itself, okay, what we call the response surface model itself, we can look into that. Okay, but in ANSYS, basically once you build it, okay, and then once you have set the design constraint itself, then it will help us to determine by itself. So we do not really need to go and explore this response surface. Okay, ANSYS will help us to explore the response surface that fulfilling our design constraints. All right. So the important thing is from the design, the flow is from design of experiments, DOE, okay, it will run a series of simulations based on the different design scenarios. So here, the minimum design scenario through this CCD, phase center CCD, then it will come out with a minimum design scenario. So a minimum experimental run to come out with the response. So from this minimum design scenario and the response, that simulated response, it will basically build the design space or the model. Okay, this model is what we call through this response surface modeling. Okay, so from the response surface modeling, basically we can build the relationship between the design variable and the response. So once we can from here itself, we can set the design constraint that we would want, okay, on our state variables, okay, our response, on our response itself, we want to set the constraint itself. So from there, okay, from the design constraint that we set on the state variable, on the output itself, together with this response surface, then we can find our input of design variable that's suitable, that fulfill the what we call the design constraint. Right, so that is the whole the procedure. So parametric optimization, because we have built the response surface models, okay, so in this optimizer, a designer set up the design objective or your constraints. So objective could be minimizing your weights, okay, then constraint will be on your constraint on the state variable or the response. So it could be multiple objectives, not only single objective, it could be few objectives. So I want to fulfill minimizing the weight. I want the response. Okay, I want the response to be as low as 0.3 mm. That I want my safety factor above 3. Okay, so this can be my objective function. So we are minimizing the objective functions to fulfill that particular the constraints. Okay, so here it could be multiple objective. So we can specify multiple objectives. So based on this fitted response surface model, okay, then it will help us to find a regions, okay, feasible region of this particular surface, response surface, that fulfilling or satisfying all the design constraints. Okay, that we would want. Right? Of course, it will come out with the best candidate, best design candidates lah. So if my design variable is my height, my thickness, my width itself, then it will help me to find a set of parameters or on the most optimum height, a set of height, uh, uh, thickness, and the width itself that can fulfill these particular objective functions. Right? So that is the whole idea of parametric optimization. It's more detailed and of so-called optimization compared to topologies. Okay, topology gives us an initial concepts, right? On our design itself. Okay, what should it look like? So, okay, and you do not really have any ideas. Okay, what your design shape should be look like. Then you perform topologies. All right. So once topology is done, you have come out with the shape itself. Then performing the analysis itself, then you want that analysis to fulfill some design criteria, for example, safety factor itself. Then you perform parametric optimizations to help you to further optimize, okay, our design. Okay, so that is the general concept of design optimizations.